All right, let's get right into it. When you see a metal part that's failed, you probably think it's from years of wear and tear, right? Maybe some big impact. But what if I told you that for most castings, the entire story, whether it succeeds or fails, is written in the first minute of its life? Yeah, you heard that right. Most defects aren't made, they're born, right in that invisible, chaotic moment of solidification.
I mean, just look at this cracked flange. It's so easy to point fingers at the material or maybe the design, but this crack, this isn't a story about a part failing in the field. This is a birth defect. Its fate was sealed the instant that liquid iron turned solid. It was a predictable result of things that were happening at a totally microscopic level. So that's the big question, isn't it? How can something this disastrous be decided so fast? And more importantly, how can it happen where we can't even see it? Well, to figure that out, we have to go right back to the very beginning, to the moment of creation.
To really get a handle on these big, visible problems, we have to zoom in. I mean, way, way in. We need to watch the tiny, microscopic drama that plays out as that liquid metal finally becomes a solid. This is where the story of every single casting actually begins.
Okay, so it all kicks off with two really basic processes, nucleation and growth. You can think of it like building a house, you know? First, you've got to lay the foundation. That's nucleation. And then you build the rest of the house on top of it. That's growth. And the quality of both of those steps is what determines how strong the final house is going to be.
Now, you might think nucleation happens in some perfectly pure, clean liquid, but nope. In reality, the seeds for these new crystals are usually tiny little impurities that are already there, things like oxides, sulfides, or nitrides. They basically act as these little launch pads, kicking off the whole solidification party. Without them, the whole structure would look totally different. So once those seeds are there, the crystals start to grow, and they form these tree-like branches of a high-temperature iron structure called austenite. This whole thing creates what we call a mushy zone. It's this semi-solid slush of austenite dendrites and graphite. Just picture a half-frozen drink from a convenience store. It's not liquid, but it's not quite solid either, and it gets harder and harder for any leftover liquid to flow through it. Now that restriction of flow, that's a huge deal. We'll come back to that. And this is where the style of that growth is everything. On the left, you've got gray iron, where the graphite grows in these interconnected flakes. And those flakes, they act like tiny built-in weak points. But on the right, you see ductile iron. The graphite grows as these nice, separate little spheres, or nodules. And just that change in shape, boom, it completely transforms the material, making it way tougher, way more resilient. It's basically the same chemistry, but you get a totally different result, all decided by how those crystals decided to grow. So while all this growing is going on, there's this epic battle happening just under the surface. You've got two incredibly powerful forces pulling in opposite directions. And whoever wins this fight determines if the casting is going to be solid or full of holes. So on one side, you have liquid shrinkage. It's just physics 101, right? As metal cools down and solidifies, it gets denser and it shrinks, pulling inward. But at the exact same time, you have graphite expansion. The graphite that's forming has a really low density, and it creates this powerful push outwards. So you've got this intense internal tug-of-war. The iron structure is shrinking in while the graphite inside it is pushing out. And here's the bottom line. The final integrity, the soundness of that part, it all comes down to the balance between these two forces. If that graphite expansion can perfectly cancel out the liquid shrinkage, you get a beautiful, solid casting. But if that balance is off, you are heading for trouble. It's a good question, right? What's the actual real-world consequence when that powerful inward pull of shrinkage just overpowers the outward push of expansion? Well, this is what you get, microporosity. Remember that slushy, mushy zone we were talking about? When shrinkage wins, it literally rips open tiny little gaps between those interlocking crystal branches. And if that mushy zone is too thick, fresh liquid metal can't get in there to fill those voids. What you're left with is a sponge-like network of microscopic holes, a hidden weakness, born directly from losing that battle. Now, all of this whole drama, it's happening in a fraction of a second, deep inside a glowing, molten liquid. There's no way to see it. So how could we possibly control it? Well, it turns out we can listen. We can actually monitor the heartbeat of the solidifying metal. And the technique that lets us do this is called thermal analysis. It's basically our window into this secret world.
By taking a super precise measurement of a sample's temperature as it cools, we get this unique signature, a story that tells us exactly what's happening on the microscopic level as it's happening. And this is what that heartbeat looks like. It's called a cooling curve. On the surface, it's just a simple graph of temperature versus time. But let me tell you, this thing is packed with information. Every little dip, every plateau, every single rise on this curve, it all corresponds to a specific event, like austenite forming or graphite nucleating. The shape of this curve tells the whole story. There are two key things we're looking for here: undercooling and recalescence. Undercooling is that first dip below the actual freezing point. It tells us how much of a kick the metal needed before it would finally start to solidify. Then you get recalescence, which is this awesome little temperature spike. That's from millions of crystals suddenly forming and releasing a burst of energy, which actually reheats the metal for a split second. The size of that dip and that spike tells us a ton about the health of the melt. And here is the proof. On the left, two different cooling curves. The red one has this really deep undercooling dip. That's a huge red flag for poor nucleation. But the green curve, see how shallow that dip is? That's a sign of a really healthy, well-nucleated melt. Now look to the right. Those are the actual microstructures that resulted. The red curve gave us a coarse structure with not enough graphite nodules. The green curve, a beautiful, fine, dense structure with a high nodule count. The heartbeat predicted the final anatomy perfectly. You see? This changes everything. If we can read that cooling curve, if we can understand the heartbeat, then we're not just watching things happen anymore. We can actually step in. We can become active participants and take control of the solidification process itself. This is the absolute core of it all. Instead of finding a cracked part at the end of the production line and scratching our heads, we can watch the cooling curve in real time and know with a high degree of certainty that a defect is about to form. It lets us shift our entire mindset from repair to prevention. And we have some really powerful levers to pull. Just take a look at this graph. It shows that by simply changing how thick the casting is, which directly controls how fast it cools, we have a massive impact on the final nodule count. A thinner section cools faster, which promotes way more nucleation, which gives you a stronger part. That's a design choice that is directly engineering the microstructure. And it's not just about the cooling rate. Everything matters. The way you design the gates and risers that feed molten metal into the mold, the rigidity of the sand, the materials you use for the cores, the metal chemistry, and especially your inoculation practice, how you add those crucial seeds to the melt. All of these are levers we can use to steer the whole process toward success. This quote just nails the whole idea perfectly. We stop just looking at a chemistry report and guessing what might happen. Instead, with thermal analysis, we are directly measuring what the iron is actually doing as it solidifies. We're, in a way, just learning to listen to the graphite. And that brings us to one final kind of provocative thought. If these defects aren't just random accidents, but are actually predictable consequences of physics, then is a flaw in a casting really a flaw in the metal, or is it maybe a flaw in our thinking? By learning to read solidification, we don't just get the power to make better parts. We get the power to think about quality in a completely new way.